Alright, instead of like the method where you have to apply the formula, so I'm going to show you an alternative method where you don't have to use the formula. What we're going to do is you're going to just use algebraic manipulation just to get the a complete of square. Okay, so for example, like first I'm going to show you like where is this idea derived from. So the idea is derived from like expanding a square. For example, let's say if I have something like this, so s minus 2 to, let's not use 2, s minus 3 to the power of 2. So when we expand this, instead of like multiplying this twice, so that is an easier way to expand this. Like, what is going to be the first term? So the first term is going to be the first term after bracket being square, and s being square, that is simply going to be s square. And the middle term is going to be the whole thing being multiplied together, and the whole thing over here, when I say the whole thing, I'm referring to the s, the negative, the 3 and the 2. So instead of like treating this as a power, so we're going to treat this as a constant 2. So when I multiply s, negative, 3 and 2, so what I'm going to do is, what happens is that I will end up with a negative 6s, because 3 multiplied by 2, that's a 6 multiplied by s, that's negative 6s. And at the back, so if you notice, so this is going to be the same. If this is negative, this is also going to be negative because I multiplied the whole thing. Okay, of course they're going to be the same. But the one at the back here, the sign is always going to be positive. Why? Because the last term is going to be this number being square, and whether it's positive 3 square, that is still going to be 9. And if it's negative 3 square, it is still going to be 9. So that is why this right here is always positive. While on the other hand, these two, they are going to be the same. Okay, so actually based on this idea, so I'm going to show you the alternative method. Is actually just reversing it, doing it the other way around. Okay, let's take the previous example, previous expression that we had. So we have 2s squared plus 4s plus 6. Right, so before you use this method, first of all, what I'm going to do is make sure that the coefficient is equal 1. It's going to make your life easier that way. So here I'm going to factorize. I'm going to end up with 2 multiplied by s squared plus 2s plus 3. So that is how it's going to look like. And then 2. So now I'm going to start making a complete square out of this. Okay, I know that here. So the first term is going to be s squared. So it's going to be s squared because this is going to be s raised to the power of 2. And this 2 sign, as I mentioned just now, is going to be the same. If this is a plus, so this is also supposed to be a plus. Okay, and if you notice right now, between these two, what is the relationship between these two? Okay, so the relationship between these two is that how do I get the 3? The 3 means we are going to reverse the process. How do we get the 3? Is we divide 6 by 2. So that's what happened over here. When I wanted to know what is going to be the number that goes there, I'm going to divide this value by 2, which for this case, it is going to be 1. So here, this is going to be my square. However, it is not done yet, because if you were to expand this, you will end up with s squared plus 2 multiplied by 1 multiplied by s. That is a 2s plus 1 squared. That is going to be a 1. But I don't have a 1, but instead I have a 3. Okay, so this is going to be plus whatever number. It is supposed to equal 3, because remember, we can change the form, but the value has to be the same. Okay, let me put that away. Okay, how do I get 1 plus what number is going to equal 3? So I know that this value over here, this is going to equal 2. So that is why here I'm going to put a 2. So this is going to be a plus 2. And this is exactly what we had previously. So 2 multiplied by s plus 1 squared plus 2. So they are the same. So whether you're using the formula or using this method, they're going to give you exactly the same outcome. So let me show you another example just to make sure that you actually get the idea. Okay, another example is, let's say if I have something like this. So s squared plus 4s plus 5. Again, So I'm going to come out with a square. For this one, I don't have to factorize because my coefficient is already 1. So I'm going to create the s square. So this is going to be s. This is plus. This is also going to be plus. How do I get the number right here? I have to divide this constant by 2. So I will get 4 divided by 2. That is going to be a 2. But however, this is not done yet because I somehow have to end up with a constant 5 at the back. And if I were to expand this, I'm going to have s squared plus 4s plus 4. And how do I end up with a 5? I have to add plus 1. So it's going to be plus 1 right here. Now, these two, they are going to be equivalent. Equivalent means equal. So the form could be the same, could be different, but the value should always remain the same. Let me show you one more. Let's say if I have s squared, so minus 6s plus 1 this time. So this is going to be s minus 6 divided by 2. That is going to equal 3. And if I were to expand, I'm going to have s squared minus 6s plus 9. But I don't want a 9. It is supposed to be a plus 1. So therefore, how am I supposed to achieve that? I'm going to minus 8. So that is going to be my complete square. That's it. However, if you're not comfortable with this, like if some like this actually scare you and confused you, no problem. Simply stick to the formula. Okay, let me start with the first example. So the first example here, I'm going to start our theorem, inversion of a shift theorem. So I'm going to find the Laplace inverse of 1 over s plus 2 squared. Again, why are we using this method? Because I have this s plus 2, s plus a. Remember, I mentioned just now, when you have something in terms of s plus or minus a at the denominator, then yes, automatically it is possible to use inversion of a shift theorem. And let me warn you, this is not equivalent to 1 over s squared plus 4. That is different. Do not simply expand this and become this and simply use the table. It doesn't work. S plus 1 squared is actually s squared plus 2s plus 4. It is not equal to s squared plus 4. So don't give me anything like that for the final exam. I'm going to be super pissed. Okay, so let's start with this. So let me put the theorem here just to remind you. So the theorem states that if we have a Laplace inverse f of s plus a, so that is going to equal exponential of negative at multiplied by f of t. And for this case right away, we can identify that the value of a, that is going to equal 2. And whatever that goes between the curly bracket, so that is going to be defined by f of s plus a, which is 2 for this case. And that is going to equal 1 over s plus 2 square. So this will be a match between these two. This is plus 2. This is going to be s plus 2 as well, right? So what I'm going to do next is that I am supposed to convert this to a function of f of s. And I mentioned before, this is going to be the same idea that we do for second shift theorem. So converting s plus 2 to s, all we have to do is minus 2. So therefore, my function is going to be convert whenever every single time I come across s in the function. So that is going to be written as s minus 2. So therefore, there goes my s. There's only 1. So this is going to be 1 over. So this is going to be s minus 2. And then I'm going to have plus 2 square. Right? And I'm going to simplify this, for which I will end up with 1 over s minus 2 plus 2. That is going to be 1 over s square. So if you don't understand how do I go from here to here, so please revisit the inversion of not inversion, it's the second shift theorem. So where I show in detail the algebraic manipulation. I'm not going to show you again. So it's going to be the same thing. Okay, that is going to be 1 over s square. And now the next step is I'll be converting this to f of t. So f of t is simply going to be the Laplace inverse of 1 over s square. And according to the table, this is simply going to equal t. So that is going to be my function f of t. However, remember, this is not yet your solution, because this is going to be our solution. You're supposed to combine that with the exponential. Okay, so now I'm going to write that. So therefore, so according to the theorem, so if I Laplace inverse the function of 1 over s plus 2 square, so that is going to equal exponential of negative a, which is going to equal 2, multiplied by t. So yes, that's right. So that's for the power, multiplied by f of t, which for this case is going to equal t. So that will be the final outcome. So Laplace inverse of 1 over s plus 2 squared, that is going to equal exponential of negative 2t, so multiplied by t. However, I forgot to mention something else just now about the theorem. So this theorem, if you notice, they are the opposite. When this is a plus, this is going to be a minus. This will be the same idea for inversion of first shift theorem. So what if this is a minus? So therefore, if you have Laplace inverse of f of s minus a, automatically it's going to be an inverse as well. So you're going to end up with exponential of positive at multiplied by f of t. Remember, according to the theorem, if this is the inverse, automatically when you change, so they are going to be the inverse as well. So let me get to the second theorem. So I'm going to find the Laplace inverse of this function. So 2s plus 1 over s minus 1 squared plus 4. So the same idea. So first of all, I'm going to start by identifying the value of a. As I mentioned just now, it is always from the denominator, for which find the bracket in terms of s plus or minus a constant. And for this case, our constant is going to equal a value of 1. So my a is equal 1. So my function is going to be f of s minus 1 is going to equal 2s plus 1 over s minus 1 square plus 4. These two, they always match. This is s minus 1, this is going to be s minus 1 as well, because that is how we derive it. We identify the value of a. And then, of course, the next step is converting this to a function of f of s. And how do we convert from s minus 1 to s? So we have 2 plus 1. So therefore, everywhere you come across s in the function, so we have 2 for this case, so that will be s plus 1. So now, at the top, I'm going to have to put a bracket around before you put the plus 1. So let me highlight that, so it's going to be more visible for us. Okay, so put a bracket around, then only put the s plus 1, and then I'm going to have a plus 1 at the back from the function itself, from the original function. And then let me put a different bracket, so I'm going to have again s plus 1 minus 1 square plus 4. So here what happens is that whenever I come across s in the function, so that is being converted to s plus 1, okay, because we're changing the function. We have to make it the same. And before you Laplace inverse, of course, you have to simplify them, unless you can actually Laplace inverse them in that form. When I simplify this, I'll end up with 2s plus 3, so that's 2 plus 1, a 3. And at the bottom, I'm going to end up with s plus 1 minus 1, that is going to be s squared plus 4. So we come across something like this already before, when I show you the example for elementary function inverse. So my f of t is simply going to be the Laplace inverse of two terms. So the first one is going to be 2s over s squared plus 2 squared, because I know this is going to be cos. And the other one is going to be sine, which is given as 3 over s squared plus 4. Right? So I have a feeling that I won't have enough space for this. So let me write that again. I'm going to write it a little bit at the back. So this is going to be a Laplace inverse of 2s over s squared plus 2 squared. That's our cosine function. And the other one is the Laplace inverse of 3 over s squared plus 2 squared. So that will be converted to a sine. Okay, however, so this will automatically, the 2, we can actually bring it out. Remember, linearity theorem. When I bring that out using the table, I am going to end up with 2 cos of 2t, because my a value is equal to 2. But this one is going to be a problem. So the reason is that here I have a equal to 2 at the bottom, but I don't have 2 at the top. So this is when you have to modify your function. So I'm going to create a 2 by multiplying this by 2 over 2. So I've shown you this in detail during the previous topic. So go and revisit that if you don't remember. And I don't need these two numbers, 3 and 1 over 2. So what I can do is I can move that to the front according to the linearity theorem. And this will end up as being 3 over 2 sine of 2t. Again, not the final answer. So Laplace inverse of, what do I have? 2s plus 1. So 2s plus 1 over what goes on top, but at the bottom, s minus 1 square plus 4. So that is going to be equivalent to, remember, this is f of s minus a. So this is actually the formula that I've just written. When this is minus, so this is going to be a positive of exponential. So therefore I'm going to have exponential of positive a, and for this case my a value is going to equal 1. So I'm going to have exponential positive 1t. So multiply it by 2 cos of 2t plus 3 over 2 sine of 2t. So that will be the end answer of that. So that is going to be the second one. Okay, now we have the last example, which is the third one. I'm going to find the Laplace inverse of s plus 3 over s squared plus 6s plus 13. So actually there is a slight difference between this example and the previous two. So can you tell what is going to be the value of a for this one when we look at the bottom? So there is no way we can tell that. Again, I told you it has to be a bracket in terms of s plus or minus a constant, which is none for this case. But remember, what we can do is when we come across something like this, if the bracket is not there, we can create the bracket. How do we do so? So that is when we're going to use the completing the square concept. Now let's change this form. So according to what we have seen before, so this is equivalent to Laplace inverse of s plus 3 over, and I'm going to use my completing the square skill, s plus 6 divided by 2, that is going to be a 3 square. And if I were to expand this, I'm going to have s square plus 6s plus 9. I don't need a 9, I wanted a 13. So therefore I have to add 4. 9 plus 4, that is going to equal 13. Alright, so basically that is going to be my function. Alright, so let's start with the calculation. First of all, I identify here my a value is going to equal 3. So my function f of s plus 3 is going to equal s plus 3 over s plus 3 square plus 4. It's going to be very simple. And then I'll be converting this to a function f of s according to what we have seen before. So this is going to be s if I minus 3 the function, and there are going to be two places that I'm going to substitute, right there, top and bottom. And now both of them are going to be converted to s minus 3. So put a bracket around s minus 3 plus 3 over, and then I'm going to have another bracket, so s minus 3 plus 3 square plus 4. So when I simplify, I'll end up with s over s square plus 4. So this is a very simple function, and I know that my f of t is going to be a Laplace inverse of this, which according to the table is just cos of 2t. So therefore, according to the theorem, so Laplace inverse of whatever that I had just now, s plus 3 over s squared plus 6s plus 13, right? So here, this is a plus. The exponential is going to be to the power of negative. I'm going to have exponential of negative 3t multiplied by cos of 2t. Alright, so that will be the outcome of this. Okay, so that is actually not a very simple, not a problematic theorem. It's not that complicated. It's pretty easy. But you have to use back the skill that you have discussed in the previous video, in the previous subtopic, right? And you have to be good at completing the square as well, because it's a very common thing for this topic too, is completing the square. Okay, so try the exercise that you have in the book, and for my students I've prepared for you extra exercise as well, provided in the PDF file. So I'll see you in the next